Hello. Good at okay. Oh, wait. Okay. Good. Yes. Hello, Vicky. Hello, Aminata. Hello, Victoria. Wait, I'm catching it. Hello, Lear. Hello, Victoria. Hello, Joel. Hello, Sonam. Hello, Gabriel. Hello, Bridget. Hello. Now doing the chat. Who did I just lose? Okay. Good afternoon, Vicky, for the double. Good afternoon, Victoria, for the double and the triple exclamation point. The enthusiasm is overwhelming. I'll try to match it by yelling. Good afternoon, Aminata, for the double and the exclamation point. More enthusiasm. I'm yelling. Good afternoon, Speed. Good afternoon, Zoe. More exclamation points. I love the exclamation points. Good afternoon, Joel, for the double. Hello, Anthony, who is named Anthony today, which is totally helpful. Thank you. Wait, who is Anthony? No, wait, I see him, but I don't. Wait. Oh, got it. Right. Good afternoon, Latchman. Good afternoon, Gabriel. Good afternoon, Roger. Good afternoon, Caitlin, with the double exclamation point. And
Good afternoon, Professor.
good
Good
afternoon.
question, though.
Yeah. Okay. Yes. Question. Yes.
Are you going to go over homework six? If you are not, can you please go over homework six? Because that last question was troubling for me.
That is the most fair question ever. I'm laughing. I'm not laughing at you. I'm laughing because you definitely just have. First of all, you should submit for points to the Please Go Forward portal because you just sped me up. Because when I finish the hellos, yes, exactly. The plan for today is literally exactly to walk through homework six. I
Thank you. Thank you.
Thank you. You just made my life feel worthwhile. Yes, that is exactly what I'm about to do. No, I'm laughing just because that's so perfect. No, I'm glad that I could do something that's like actually helpful. That yes. Okay, so yes, that's good. Yes. So I'm just gonna finish saying hellos. And yeah, and by the way, yeah, homework six, it is hard. It does get hard. I mean that and okay, I'm gonna stop. Yes, that's exactly what I'm about to do. Um, what just happened? So hello. Okay, good afternoon, Gabriel. Good hat for the double. Good afternoon, Roger. Good after. Oh no, I was already there. Sorry, Sanam. Good afternoon for the double. Good afternoon, Caitlin with the double exclamation point and the emoji. That's where I was. Good afternoon. No, not emoji. Whatever. Good afternoon, Spencer. Which is not Spencer. It's really, I know who it is. Don't tell me. I know it's I really should be getting to know your names better at this point, especially because you're physics 204. So don't tell me. Wait, I know who Spencer is really. Don't tell me. Oh, Raina, right. Sorry, it's Raina. Yeah. Okay. Um, And no problem, Anthony. Yeah, no. It's fine. Oh, did you just change it and think? Cool. It's not, thank you. I mean, that is helpful. Yeah, it's not like you're bad that you didn't do that, but it is good that you did do that. Thank you. Okay. And okay, so that's everybody. Oh, and David is in the waiting room. Okay. So yeah, I will try to get rolling now. Yeah, I honestly, I mean, joking aside, I want to get straight to exactly what Melanie just asked. And I hope you'll see it. It's perfect that Melanie asked that but it's not just because Melanie asked it. Like the plan for today is to talk you through homework six. Um, it is hard, but it's very important. Or it looks harder than it is, but it does look hard. And it is an involved calculation. As soon as we start this in a minute, it is going to take us the whole period. I'm just thinking, I'm just going to quickly think if there's anything else I need to say, because once we get rolling, it is a thick computation. It's repetitive. So hopefully you'll see the point once I make the big point of what's going on, and then it sort of repeats to get answers, but it does take a while to get the answers. I'm also going to warn you that the numbers, one day the numbers don't work out nicely. One day I'll tweak it so that the numbers work out more nicely, but they just don't. So it takes some focus to do this problem. We're going to do it all together in a minute. If you've already, and we're, it's that time of the semester where we're all getting tired and maybe stressed out about grades and stuff. I am very behind. I always fall behind at this point in the semester. I'm going to try to catch up with all of you during the break. As I've mentioned, highest priority being your exams. But as I've mentioned, like everything is still in Google Classroom. Like you will get credit for everything that you deserve to get credit for, even if it's taken me a while to give you the credit. Um, I want to reassure you of that. Um, why am I saying this? Oh, so it's just a reminder, like even though it seems like things are like less tight than they often are at the beginning of a semester, everything still is in Google Classroom. So it's still the same procedures and stuff. I'm trying to say. If you're a person like Melanie, if you've even attempted this homework and you turned it in the first draft on time, because I think it was due today, right? I think, wait, I'm going to look again. I can't even remember. But if you turned in the first draft on time, no matter how much improvement you need to do on it, based on what I say today, that will be totally fine. You could totally, as always, upload a revision. It was due. Yeah, it was due right now. Right. So, all right, let me back up for a second. First of all, I'm not going to mention names, but I'm looking right now. I see that out of 25 of you, 13 of you did turn it in on time for today. And thank you and congratulations. Like, I know it gets harder and harder, especially when you're not getting things back for a while. Like, it gets harder and harder to stay on top of these things at this point. So, if you turned in anything on time, that is great and it is noted, and you will get that means that even if you make corrections based on what I now do in class today, you'll be able to get all of the points. Okay. If you didn't turn it in yet, you still totally can and should. You might not get all of the points, but you'll get a lot of points. It'll be worth still doing this, even with the benefit of what I do today. But that's like why you can't get like all the points. But also, yes, this is a problem that often appears on the final exam, even if there's choices or whatever. So it's really good to know how to do this problem. So that's all by way of encouragement of if you're going to be doing catching up during the break, as I am, some break. It's worth considering. I'm still accepting things and revisions and stuff. Okay, last announcement on that, and then I will get to this sheet. Or last announcement on that. If you're ever trying to catch up on anything in a physics class, my one recommendation or pro tip, because still all the homework portals are open, you still can, if you're looking for like, oh, I want to get more points now about this or that, you can, you're encouraged to until the last day of classes. So you can. So that means two things. Number one, I would always recommend going backwards. Don't first, if you're going to catch up or try to fill in gaps or something, don't go all the way back to homework one. At least don't start there. Like go to the most recent thing first. Try to do that or try to improve that. Then if you look at it, you're like, yeah, I don't know what's going on here because it was based on the last thing. Okay, then go to the thing before it, but go backwards, triage. And that's what I do too. Okay. I do recommend that. Number two, also recognize if I haven't said this before, we're all triaging at this point in the semester. It's always like that. Um, so if you're trying to catch up on material or points, and you look back at some old assignment, and again, I will be doing this too in my way during break, but of course my priority will be the exams. But I'm still trying to clean up all the piles and whatever. If you go back to some old homework from a while ago and you notice that you did turn it in on time and you got a bunch of points, but you didn't get all the points, I'm asking you in the name of triage, in the name of efficiency, and in the name of your optimal success, if you see an old homework that doesn't have all the points on it, but yet let's say maybe it doesn't have feedback on it yet. Very possible. Look at it. If you see at this point, because of more material that we've covered in the semester since then, or because if you could look at it and see, oh, I know why I didn't get, like, I can see why I didn't get all the point because I didn't ever do the last problem or something. Or, oh, yes, in retrospect, now that I studied for the midterm, I could see that I did this all wrong, or I wasn't even doing the 5-step method or something. If you can see a way to improve it, don't wait for the feedback. Just do it and just return it in, and I'll see it immediately, and you'll get more points. or it like to save us both a step. Or if you look at some old thing, you're trying to organize your life, and you look at some old thing and you're like, there's not all the points on this, and yet I don't see any feedback, and I really don't know what I'm supposed to do. Like, I honestly think I did everything. I solved all the problems, and I think it's all there. I don't know what the problem is. Well, yeah, then just write me a quick note and say, I'm still waiting for feedback on this one, or I'd really like to improve this one, but I don't know how. Can you please help? Right. And I will, it'll go like to the top of the pile, and I'll look at it, and maybe it's possible that I'll say, oh, no, you're right. I'm so sorry. I'm behind. You're right. I owe you the rest of the points. Done and done. And I'll just give them to you. And that's a gain for both of us. Or I'll say, oh, yes, no, you still need to do problem 5, or you didn't do the, okay. So just that's how we can work together to lift the piles for both of us. Or I mean, lift the grades and reduce the piles. Okay, that's just a logistical announcement about that, or reminder about that. So I'm going to now go over homework 6. That's all by way of saying if you turned it in, you could still improve based on what I'm about to do. Or if you didn't turn it in, you can benefit from what I'm about to do. You just can't get all the points. So yeah, so homework 6. First of all, I'm going to screen share. Wait, let me look at the chat if there's anything going on in the chat. Okay, the chat is fine. Okay, so I'm going to screen share so you know what I'm talking about. Wait, sorry. Is it sharing the right thing? Yes. Okay, so this thing that you're looking at is what Melanie was asking about. It looks intimidating, but it is a classic important problem. Oh, and there's people in the waiting room. I'm sorry. Hold on. Oh, yeah. How do I? Sorry. There's people in the waiting room. I think. Are there? Wait, I'm confused. Uh, Pardon me for a second. It seems like there's people in the waiting room, but I can't. Oh, no, there aren't. Okay. Um, okay, so we're talking about this problem. Okay, so it's going to get mathematically thick. Let me first give you the conceptual overview of what it's trying to say, or like what's going on here. Yeah, we have a Cartesian plane like in the lab, and we have point sources of electricity. We have point charges sitting in the lab, like at a certain set of coordinates at 5 comma 4, we have a point charge of positive 5 coulombs. That in effect means we have like 800 quintillion protons jammed together in a Euclidean dot, like over here in the lab. Like that's a lot of protons. It's a lot. It's kind of a round number, but it's not a preposterous amount of protons. All right, so we have a whole bunch of protons jammed together in a tiny dot, and of course protons are very small, so this isn't, beyond imagination. So you have a bunch of protons over here in the lab. Then somewhere else at coordinate um at coordinate 10 comma 3, you have a bunch of electrons jammed together. Not as many. Like you have 40% as many electrons jammed together into a tiny spot. So you got a point charge over here and a negative point charge over here in the lab. Quick sidebar, in terms of reading this problem, part of what's confusing, where it says 4/3, that's not supposed to be a like in the middle of the page where I'm looking right here. I mean, it's just saying it's not meant to be a fraction. It's just like a whiteout on the grid behind it. So it's trying to say that you have a positive charge at coordinates 5 comma 4. You have a positive charge of 5 at coordinates 5 comma 4, and you have a negative charge of 2 at coordinates 10 comma 3. That's okay. It's not meant to be a trick. It's just like a whiteout situation. So that's that. Now, so you got these charges here in the lab. I'm going to, switch screens in a second and draw the picture. But what's the point? Like, what are we about to try to talk about or solve? Well, the idea is that each one of these charges is now creating or making a contribution to what we call an electrostatic field everywhere in space. This is where we left off on Monday, that we now, as of the last minute of Monday's class, we now have a concept of something called a field, which is very related to force, but it's different. Field is force per charge. Mathematically, field is force per charge. Mathematically, field is how much force, let's say electric field is how much electric force one source charge, one capital Q1, would exert on every single positive 1 coulomb of test charge that could be at a certain distance from the original source charge. If force is measured in newtons, which it is, if electrostatic force, if any kind of force is measured in newtons, then field is measured in newtons per coulomb. If force is something that I do to you, then field is something I do to any and every point in space. Force is something that one object does to another, but field is something that one object does to space. The idea is that we used to say a proton pulls an electron electrostatically, or we used to say that the sun pulls the earth gravitationally. Now we say the proton pulls on space or pushes on space everywhere, a certain amount everywhere. And if any electron comes along to any point in space, then the electron is pulled by the field that's in that space. So field is force waiting to happen, like for real. I'll put it one last way, and then I'm going to switch the screens in a second, start doing this. But so mathematically, field is very simple at its core. I'll write the equations again in a second, or show you the equations again in a second. Mathematically, field just means force divided by charge. If a force is K times Q1 times Q2 divided by the R squared between us, or the square of R between us, if force is something that Q1 does to Q2 divided by the square of R between us, then field is just Q1 times the constant divided by R squared. Like the only difference between force and field is that force has 2 objects in it and field just has 1 object in it. Like literally, mathematically, it's only the difference. But the whole idea of field is that it's all the information of the force ready to go. It's the entire amount of the force that would be exerted on each 1 coulomb of positive charge that could be found at any given location we're looking at. It's the amount of newtons that would be exerted on each 1 coulomb of positive charge. Therefore, the minute we find some charge at that location, say we find 3 coulombs of charge at that location, we just say, aha, the total force would be field times 3. Like field is what the number of newtons that would be pulling or pushing on each 1 coulomb. But if there's 3 coulombs there, then that number of newtons is pulling on each of those 3 coulombs. So we multiply by 3. So I'm going to switch screens in a second, but I'm trying to say mathematically, field is force per charge. Therefore, the force that's exerted on some charge is simply field times charge, times that amount of charge. It is that simple. I'm not saying it's easy, but I'm saying the concept mathematically is that simple. now we're going to like put it into practice here with this problem. This problem is saying, okay, well, let's like apply it, like let's practice this, let's like, see this in action. It's saying, okay, if you've got a bunch of protons over here and you got a bunch of electrons over here, then the protons are like pushing everywhere out in the world. They're creating a field everywhere out in the world. Any moment of space, any point of space you look at in the world has got like a little vector arrow there signifying how many newtons are waiting to push or pull in a certain direction at that space. Waiting for what? Waiting for each coulomb of test charge of lowercase q to come along and experience that arrow. So Q, capital Q1 is making field vector arrows everywhere in space, but at the same time also lowercase q2 is depositing like field arrows everywhere in space. And so we're saying anywhere in space you look, there's a field arrow, a field vector from capital Q1 sitting there, but there's also a field vector from capital Q2 also sitting at that point anywhere you look. So there's like two force contributions like waiting to happen with certain amount of strength in certain direction, waiting for, they're not literally waiting. I'm not saying they're like looking at their watches, but like they're ready to go. The information is ready to go to be applied if and whenever some coulombs of test charge like land at that, like arrive at that location. So our goal here is to figure out exactly how many newtons and in what direction are waiting at some given point in space. For example, in this problem, it's asking us to focus. It's putting a field detector at the point 0, 0. So what we're going to do in this problem is we're going to compute the electrostatic field acting at the point 0, 0. We're just picking that point. We could pick any point. That's just like the easiest point to focus on. We're picking the location 0, 0 and asking, since there's an arrow there from one point source and a field arrow from the other, can we like vectorally add those arrows together and get one final arrow that indicates what the electrostatic field magnitude and direction is at the point 0, 0. That's what we're going to try to figure out. What is the field vector, the field magnitude and direction at 0, 0? There is exactly one arrow sitting at 0, 0 due to the existence of Q1 and Q2. There's a field at 0, 0 that means a number of newtons per waiting to act per each coulomb that might or might not ever arrive at 0, 0. That's what we're trying to figure out. The force per charge waiting at 0, 0. The field vector waiting at 0, 0 due to Q1 and Q2. Okay, that's what we're about to do. We have 49 minutes or 51 minutes to do it, which is fine. We will, but I want to make sure it's clear what we're doing. That's what we're doing. Yeah, so this whole sheet is asking us to do that. It's going to ask us to draw a sketch of the situation. I'm going to do that, and then compute the magnitude and direction of the E field, which is a long computation. That's what we're going to do. And again, I apologize in advance. The numbers, I'm even going to round the numbers. I'm even that number in the that universal Coulomb constant in the middle. I'm going to round that severely to make the numbers easier to work with, but they're still like annoying numbers. I there's just nothing to be done about that at this point. So okay, I'm gonna switch screens. I'm gonna switch screens. Oh, I always do. All right, so first of all, I'm going to draw the situation. Well, so this is, what is this? This is homework 6, part B. Okay, so here's the situation. I mean, it's a big Cartesian plane. It happens that everything is happening in the first quadrant. I'm not even sure why, but it is. So and I'm putting points of the compass on to make it clear what's going on. So, okay. So first of all, so we have this. And then we have this. Right. This is a situation. Now, that's a situation. Oh, and so this point, just to be clear again, this point the point zero zero, oh yeah, which I call the location of interest, is just that. It's super important in the whole problem. It's the location at which we're going to determine the field. But I want to emphasize, and so a lot of like websites and textbooks and whatever in future science situations will refer to that place as the field point. That's what people mean by a field point is the location that you're like measuring the field. But I just want to emphasize before I go on, it's just that. It's just the location where we're measuring the field. I don't want to imply that that's the only location that there is field. There's nothing special about that location. It's just a location that we're looking at. There is field everywhere, and whatever calculation I'm about to do, we could apply anywhere. Okay. So what is the anywhere that, so what do we do? So I'm going to continue with like this picture now. I'm just switching the screens again. Okay. Looking at the chat. Okay. Um, so this diagram is going to get a little crowded perhaps, but Q1, let's just focus on Q1 for a moment. I'm saying that if you focus on Q1, which is positive, I'm saying that the minute Q1 exists in the world, it creates field. It starts depositing the in oh well, hold on. Yes, I'm going to say that, but let me remind you of the equations. Like this, all of everything we're saying here is originally in the first place, it's coming from this equation. Everything is coming from that equation, but like that any one Q1 would pull or push automatically on any other Q2 in the world. But now we're advancing our understanding and saying, okay, but if that's true, if Q1 is always going to automatically pull on Q2, as long as Q1 exists and Q2 exists, like as long as their charges are in the world, they're automatically going to push or pull on each other whether there's space in between them or matter in between them. They don't have to do anything. It's a fundamental force. They're just going to automatically pull or push on each other. And they're going to pull and push on each other according to this equation. Like the bigger one of them is, the more they're push or pull. And the closer they are to each other, the more they're push or pull, which means, this is a very important thing. It means that like if they, it means that as one of them gets closer to the other, the force will change accordingly, right? I mean, it always obeys this equation. So that means that somehow Q1 always knows how far away Q2 is and how big Q2 is, like how charged magnitude it is. I don't mean knows like consciously. I'm not trying to be weird, but I am saying that if a proton is pulling on an electron with an amount of newtons that is determined by how far away that electron is, and then if the electron gets closer, now the pull is of a different strength, that means that the new address of the Q2 of the electron that just like moved, the new location of the Q2 somehow got delivered to the Q1. Like, I mean, I'm not trying to be weird, but that is weird, right? I mean, I'm saying that whatever exists over here somehow has access to the information of whatever is going on over here in space. I see there's chat. I'm going to look at the chat in 1 second. That awesome. So what I'm saying is, therefore, the best way to make sense of, I mean, that's a mind-numbing thing. Like, I don't want a rabbit hole, but like that is what we're saying. That therefore, the way to think about that, the simplest way to think about that we know to think about that and to make predictions, accurate predictions based on that, is to say, okay, the minute there's a proton in the world, even before there's any electrons or anything else in the world, the minute that Q1 is in space, it's going, and I will look at the chat in a second. I totally promise. I'm totally excited. Let me just finish this up before I forget it. What we're saying is every Q1 or every capital Q that's in the world will automatically place all of its vital stats, its information, the amount of magnitude that it is Q1 divided by the location where it is R, it multiplied by the universal constant, it's going to place an arrow containing all that information at every point in space so that the whole force is like ready to go. All the information of the force is ready to go, whether or not any other object is there in space to get it. In other words, the information is in space somehow. This information that's in space in the form of vector arrows in our mind. I mean, we don't literally think there's arrows in space, but in our mind, we picture them as arrows everywhere in space. We call that the field. So I will totally get the chat, but I'm just trying to emphasize the big equation that we're going to use for all this stuff is the second equation here. Notice the second equation is just the first equation divided by Q2 is just saying all the information of the force that will be created by a capital Q before any Q2 even comes along to experience it. So what I'm saying, I'm not forgetting the chat. I'm just actually, well, yes or no. Let me look at the chat. Okay. Hold on a second. The chat does it charge? Oh yeah, no. This is a very good question. So I'm going to read this question out loud. The good thing is, I'm really psyched, you guys, because this is like Melanie's question from before. Like, this is a great question because this is like exactly about what I was about to get to. So it shows you're with me. I mean, so the question says, does the okay, right. Well, I'm totally going to answer this. I mean, like right now, but the question, just so everybody can be together, the question says, does the charge, like +5 or -2 or whatever, does it indicate the direction in which the arrow would be on the lines, if that makes sense? And the answer is yes. That's exactly what I'm about to show you. Like, we're going to put arrows on the lines that totally are determined by those charge numbers. Yes. I'm assuming you would also need angles. Yes, I'm going to do angles in a minute in order to find the directions in relation to one another. Right, exactly. But I was wondering how the magnitude of Q is incorporated into this. Okay, so that's exactly what I'm going to show you. And someone drew the diagram earlier, but was confused, like how to incorporate the charge into the. Okay, so sorry, I should be. So someone's basically asking, like, how do these facts like turn into a diagram? How do these facts turn into arrows that we can like do anything with? Perfect. Thinking like a physicist. Perfect. So that's what I'm going to show you right now. So look, if you focus on the Q1 first, on the capital Q1, what I'm saying, and this picture will get a little complicated. I'll probably like rewrite the picture a couple times. What I'm saying is that the Q1 at every point in space it is placed at every point in space. Now, I'm just drawing a bunch of representative arrows at first, just to show you the pattern. I'm saying that if Q1 creates a contribution to the field, that means it puts arrows everywhere in space, everywhere. At every point in space, there is an arrow, including like right here. Oops, sorry. At every point in space you look at, there's an arrow caused by the Q1. Notice, and I'm about to do the arrows for Q2 as well in a moment, but just notice, everybody, notice something about that's just enough arrows to show you the pattern. And what is the pattern? The pattern is that wherever you are in space, first of all, there's an arrow sitting in space that's pointing along a radial line away, directly away from Q1. Why are the arrows all pointing away from Q1? Because Q1 is positive, which is partly like an answer to this person's question. Q1 is positive, and so it's making field, and field is always a prediction or a computation of what will happen or what would happen to every coulomb, every 1 coulomb of positive charge that could ever be located at any point in space that you're looking at. So the field is a prediction of what would happen to positive charges. So since this source is itself positive, it would necessarily push out on other positives. So arrows coming from a positive charge, a positive source, a capital letter, arrows coming from a capital letter are always going out. They're always pushes because the attest charge is always assumed to be positive. The receiving charge is always assumed to be positive. So we're diagramming what a positive would do to so we're diagramming what would happen to a positive. And in this case, the thing that's doing it is positive. Hold on, I'm going to look at it. So all the arrows are pointing out from this positive source. And notice also, before I go back to the chat, also notice that the arrows are getting shorter and shorter as you get farther and farther away. That's like not an accident, because r squared is in the denominator. The farther away you go, the weaker the push would be from a given point charge, right? Now, I'm going to look at the chat, but let me also rush to say Q2 is doing the same type of thing at the same time. Only two differences. One, all of its arrows should be like 40% shorter than Q1's arrows. Now, that's going to be sort of hard for me to do exactly with my hand. You know, it's all better on a computer or when you, but in principle, any arrows that I draw for Q2 now, like in the same relative spaces, are going to be like 40% shorter. I say 40% because it's got a magnitude of 2 coulombs rather than 5 coulombs, right? But also, Q2 is a negative source. But we're always drawing what would happen to a positive test, a positive receiver. So that's the convention. What would happen to each 1 coulomb of positive charge? Therefore, the Q2, therefore a negative source, will pull in. So I'm glad a lot of things are happening in the chat. That is very good and exciting to me. Let me just, before I get to it, I'm going to draw the arrows now from the Q2. In principle, they should be shorter, although I didn't give myself a lot of space to do that. And then they get shorter and shorter as you go, right? Just like the other ones. So it's just like the other pattern, sorry, but they should be shorter arrows even right from the get-go. And they're going in rather than out because Q2 is a negative. And yes, eventually, eventually there's some little arrow over here pointing to Q2 that would be shorter than the red arrow that's pointing away, right? And ultimately what we're going to try to do, it's a little hard to, let me just get this. Ultimately, our whole goal of this whole problem is to add we're focusing in on here, we're going to try to add that red arrow to that blue arrow and vectorally and get a total arrow, the one total resultant vector that is acting on the origin as a result of the red push and the blue pull. That's what we're trying to do and analyze. We could have picked any point, but we're picking that point. That's the idea that's going on. Okay, now, and that's what we're going to do. I'm looking at that. We'll be fine, 33 minutes, but what's great, I'm so glad you guys are asking questions and following this. So let me look at, so there is stuff in the chat. So let me look, hold on. I get it now. I don't know why I drew my diagram the way I did. Sorry, I should, so I get it now. That makes me so happy. So you should totally submit for points. I think another, oh. Okay, I'm not going to read all of this. It may confuse some of you, but the person is anticipating also another step. Like, let me say, what we're doing right now is thinking of fields as vectors. We're totally understanding them as vectors right now and thinking them as a field, as a bunch of vectors everywhere in space. And then we're going to add two vectors together and get the answer here. What the person in the chat is anticipating, there are other ways to draw fields, and we're going to do them next. And yes, they are more common and more useful for more complicated situations. They're called field lines. I think that's what the person is talking about in the chat. There's a thing called field lines, totally, and they can curve and bend. They look different. We're going to do those next. Totally important, totally huge, but they come from this, and they're very hard to understand unless we understand this first. So we're doing that next. But yes, if a person who's writing to me like was sort of trying to do that, I mean, that's not crazy. All the power to you, but that also is not as useful for a situation like this where you just have 2 points. It's better to think of it in terms of vectors. But yes, you're not crazy, and we're going to do that next. So that's why we're in a class together. Okay. Got it. Cool. Okay, but then someone else is in the chat, which is great. Q2. Oh, I think I just, okay. So now someone else in the chat is asking, in Q2, the charge is negative. Yes. Well, I'm going to pause. Okay, it says in Q2, capital Q2, the charge is negative. It says that, and I agree. And let me pause before I go any further and say that is why my blue arrows that are caused by Q2 all point in, since Q2 is negative. Like, that's a truism. We can all like field vectors from positive sources point out, and field vectors from negative sources point in always, because the field vector is representing what would happen or will happen to some positive test charge of 1 coulomb. Okay, yes. So I'm capturing the positivity and the negativity in my picture here. But then the person in the chat then says something interesting, says, could I explain the relationship between Q1 and Q2 in the XY plane? Now, that's a very interesting question and a very fair question, but I want to be very clear about the answer. So they're asking what's going on between Q1 and Q2. My simple answer is, I don't mean this sarcastically. My simple answer is, I don't know and I don't care. Okay, of course I do care, and actually I do know, but I want to be clear before I rabbit hole or like get confusing. This problem is not about that. That may be an interesting question, but this problem is very deliberately trying to get us to see that every object in the world creates a field like somewhere else. Every object acts like a source of pushing or pulling. Push, and so every object in the world starts pushing or pulling everywhere in space. And if there's more than one object in space, then more than one object is doing that. What we're interested in here is we're saying, wait a minute, if capital Q1 is the source of field activity and Q2 is the source of field activity, which it is, we're here trying to figure out what is the net effect of Q1 and Q2 acting on space. For example, on the point of space 0, 0, we're examining the point 0, 0 to say, what is the field there due to the combined activity the combined existence of Q1 and Q2, treating both Q1 and Q2 as sources, as field sources. What is the resulting field over here? So it's very important to understand. And I'm not saying the person who's asking this doesn't understand this. They may be saying, yeah, I get that, but I want to know something else. That's fine. But let me make clear to because this is a common thing to everybody. Q1 and Q2 are both made capital letters here because we're regarding them as both the sources of a field, and we're asking what's the and we're trying to do the superposition of field contributions. We're trying to figure out what the field is over here due to their combined effect. In no way in this problem are we in any way analyzing like what one is doing to the other. Now, could we? Oh, sure. Now, to answer the person's question, just to be clear, we totally could analyze what the Q1 is doing to the Q2. And the way we would do it is we would literally just apply the equation at we would just apply the force equation that's written here on the sheet. Literally, we would just plug in Q1 and Q2 and just figure out the R between them and square it, like literally. And that would be the effect of one on the other. And the only reason I'm not doing that is, in effect, that's what we did on Monday for practice on the front side of the sheet. Like, we can do that, but we've already been there, done that. And I'm not being sarcastic. And I actually hope the person acknowledges in the chat privately, like whether I'm addressing their question or not, because it's an important one. But I feel that's what we already did in part A. What we're now doing is actually something harder. We're going to say, now let's put them together as, and figure out what their combined effect on something else is. So, okay, that's maybe tell me in the chat whether that, but anyway, that's what we're about to do. So, and you can tell me to go back if you want, but so on the point 0, 0, what we have so far is we're like looking we have like contribution 1 going like that, and we have contribution 2 going like that, right? Like E1 was pointing away from Q1 and E2 is pointing toward Q2. Oh, thank you, person in direct chat who just said that I just cleared up a lot of confusion. No, that really helps me a lot to know that, and I'm relieved. And please submit for points that you just did that seriously, but good. Okay, thank you. Because that, for what it's worth, people, when I go down these, when I answer these questions like that, I mean, I'm believing in my mind it's not just that person that's asking that I'm talking to, and I believe generally they're articulating something that a lot of people don't even know is confusing them, but is, whether they know it or not. And I will definitely tell you that the specific thing that the person just asked that I just talked about, like that it's not them affecting each other, it's affect. Oh, did that confuse me for so long when I was in college? But I didn't know that that's what was confusing me. All of this stuff is real. Like none of you, okay? Like it's a journey. We're all in it together. None of this stuff is obvious. If I understand it now, it's because I've thought about it so many times. It's not because it immediately made sense to me. And I was like signing up for this. Anyway, you know what I'm saying. So we're adding up. What we want to do is add up the effect of the red arrow with the blue arrow that's happening over here. Okay, and notice right from the get-go, I hope you understand that their directions were totally determined by where, like those arrows right there. If you really understand what I'm saying, or like physically picturing what I'm saying, like that red arrow is literally a bunch of information. Like if I did this all perfectly to scale, right, that red arrow is pointing in a certain direction and has a certain length. It's literally the bundle of facts that represent the existence of Q1, specifically not just the existence. And that bundle, that red arrow is literally saying Q1 is this big, it's charged in this way, and it's over there, right? Like that's what red arrow is saying. There's a Q1 over there that's this big. And then the blue arrow is saying to space, is sitting in space saying, oh, also there's a Q2 over there. Oh, over there, don't forget. And it's saying, but like that one's pulling over to that location, and it's pulling a lot less then the A1, like specifically the blue arrow is deliberately shorter than the red arrow. And if I were doing this all with a computer program or like really to scale, it would be perfectly to scale. It would like literally convey the fact, like, why do I know that the blue arrow is shorter? Because first of all, Q2 is weaker than Q1. I mean, it's a smaller charge magnitude. It goes into the numerator of the equation. It's weaker charge, so it's going to be a weaker, smaller force. Also, Q2 is much farther away. So the R in the denominator is much bigger. So like for sure, I know in advance, there's a pull and a push happening in different directions, but the pull is most assuredly weaker than the push. Okay. And now we want to get the combined effect of these on the field point on the location of interest 0, 0. So before I go any further, so these are two vectors. So all I'm going to do now, I mean, all of this talk, okay, we got 23 minutes. All of this talk was to try to get you to picture what's going on, which was like Melanie's original question, super legit. Like, what the hell is what is going on with fields? It's hard to picture until you get used to it. That's what I'm trying to help you do. But once you're picturing the situation, now all we're doing now, the rest of the math for 23 minutes is going to be that we're just adding two vectors to get a third vector. That's literally, it's just that we're adding field vectors. So when we add vectors, we always place them tip to tail, right? In order to picture what's happening here, when you add vectors of any kind, you place them tip to tail to see their combined. The missing vector is the resultant, total vector. So I'm going to place these tip to tail. I'm just zooming up just so you can picture what's going on. I'm just, blowing up the diagram. And so the answer that we're trying to get will go from the original tail to the final tip, right? Like be careful, like tips and tails matter. The final answer that we get or that we're looking for is that yellow arrow. Like if I drew all this perfectly to scale, this is going back to like lab 3, or excuse me, lab 3 of physics 203, like when you do everything, draw on the graph paper and all that. If I did all this, if I drew all this perfectly to scale, then this picture right here would give me the answer. Like literally, the length of E of the yellow arrow would be the number of newtons per coulomb, would be the magnitude of the field that's occurring at 0, 0. And the direction, the angle of E would be the direction of the answer. Like if I drew it perfectly, then my drawing would be the answer. Now, I didn't draw it perfectly, and I need to show you how to do it analytically. But one thing, if this diagram is at all reasonably drawn, if nothing else, it's sort of indicating to me that in the final analysis, the answer for the electrostatic field should push or pull southwest. Like that's what the picture seems to indicate. And it's right. Like meaning, and it sort of makes sense, right? Because E1 points southwest and E2 doesn't, but E2 is so much smaller than E1. It's sort of not shocking. Like if you just look at the picture, like E2 is going to make our final answer be different from E1. Like E2 is going to like shove E1 a little bit, make it a little shorter, point it a little bit more south than it already point. Well, that doesn't make sense. Make it point a little less south than it points. Yeah. It's going to make it point a little less south than it points, and it's going to make it point a little bit less west than it points. But it's going to still, the final answer probably going to point southwest. So when I get a final answer, if my angle is southwest, it's a good sign that I've not made, it's like a way of checking myself. If my final answer doesn't point southwest, something's wrong somewhere. Okay, so now I have 19 minutes. I literally have to do the computation. So how are we going to do this? Um, we're going to do the same thing that we ever did with displacement vectors or velocity vectors like last semester. We're going to add by the component method. We're going to add up all the x components individually, independently, and add up all the y components independently. So I'm going to zoom. So I've got 17 minutes. So I'm going to zoom in on each. I'm going to zoom in on each vector individually and resolve it into components, right? This is exact. So now I'm doing math. Now, like this is literally, if we understood what we did with that, and it's just like first we did it with displacement vectors like in lab 3, then we did with velocity vectors, and we tried to emphasize it's the exact same procedure, but it was like harder to picture, like in the midterm of physics 203, if you remember, like with velocity vectors, same math, but harder to picture exactly what it means physically. Say again here now too, same math, harder to picture what it means physically. That's why we're talking about it so much, but same math. So I'm going to zoom in on E1. Here's E1, right? I mean, very southwest. Right? Now, so what is it? What is E1? It's, if it's southwest, it's some amount west and it's some amount south, right? And there's some angle here. Specifically, this would be the cosine component of E1, and this would be the sine component of E1, right? So we're going to get, so what is that? Well, so this is like the x, so I'm going to get the x component and the y component of E1. E1x is going to equal E1 cosine theta. What do I mean by E1? Okay. E1 is, well, now I'm going to, 15 minutes. I'm going to, E1, well, remember, the equation I'm using is that in general, E equals that constant times charge, times charge over distance squared. And so I'm drawing triangles and tips and tails to indicate direction. So now trying to get the components, so I'm just looking at magnitudes. So I'm going to get magnitudes of components, like just raw lengths of the triangle sides. So E1 is that constant 1 over 4 pi, which I'm going to round to 1 times 10 to the 10th. Then Q1 is 5. And r squared means r means distance from the origin from 0, 0. Well, Pythagorean theorem, it's it's 5 squared plus 4 squared. Okay, there's 14 minutes left. I want you to focus for a minute and make sure. I'm going to do the thing I'm doing right now. Once you understand it, I'm going to do it 4 times and put them all together. And so the other 3 times I'm going to do faster. So make sure put in the chat if you don't understand what I'm doing right now. I'm saying E1 is that constant, like that's this right here, times the charge. And I'm saying 5 squared plus 4 squared is r squared, right? Because of the original coordinates that were given. Like Q1 is 5 along the x-axis away from 0, 0, and it's 4 along the y-axis, right? So its total r is the square root of 5 squared plus 4 squared. Its total r squared is 5 squared. Okay, I'm doing the distance formula. I'm doing Pythagorean theorem. Stop me if you don't understand that. That's that. So then what's cosine of theta? Now follow me on this. Cosine of theta. Well, what's theta, you might say? Well, I could get it by doing reverse trigonometry and all that, but I'm going to cut straight to the chase. To get the cosine of theta equals adjacent over hypotenuse, right? And sine of theta equals opposite over hypotenuse, etc. So what's the adjacent? So again, look at this. I mean, look at this. The adjacent of that triangle is the 5. The triangle I'm talking about. I don't want to get this diagram is getting very, but the diagram I'm talking about, I mean, the triangle I'm talking about is this. Well, no, actually, I mean, it is, but hold on. The way I'm drawing it, it's this. This is the triangle I'm talking about. So the adjacent is 5. The opposite is 4. The hypotenuse is square root of 5 squared plus 4 squared. So the cosine is adjacent over hypotenuse. The cosine is 4 over square root of 5 squared plus 4 squared. Okay? Cosine is adjacent over hypotenuse. I never had to get the angle. I'm just cutting straight to the chase. So I'm saying in summary, E1x equals 1 times 10 to the 10th times 5 all over 5 squared plus 4 squared times 5 over square root of 5 squared plus 4 squared, right? That's E1x. There's 11 minutes left. So I'm going to do them. So it's 25 times 10 to the 10th. That's the numerator. All over 41, like 5 squared is 25 plus 16 is 41 to the 3/2 power, right? It's 41 times the square root of 41. It's 41 to the 1th times, you think that through, but it's like remember, square root means to the 1/2 power. So this whole number is a bad number. It's not a bad number. It's an annoying number. But it is approximately. Well, actually, okay, let's. Okay. Okay, so you get 9.51 times 10 to the 8th What is that? 9.51. We have 9 minutes left. 9.51 times 10 to the eighth newtons per coulomb. That's not an answer to the whole problem, but it's like the most important piece of information in a way. That's E1x. That is how hard the Q1 is pushing to the west on the x-axis on every 1 coulomb of charge that could ever be at the field point, right? That's the horizontal component of field due to Q1. So we have three other things to do. The next thing to do is, but they're all going to be like the same procedure, is to get E1y. Okay, E1y will be the same number, will be the same kind of thing. 1 times 10 to the 10th. So I'm, going to go faster and faster. 1 times 10 to the 10th times the same charge, which is 5, over the same uh distance, 41, distance squared, 41. But now times the sine. Okay, I'll say this quickly. I got the power 3/2. Someone asked in the chat, because this is 41 and this is 41 square rooted, or in other words, 41 to the 1/2. So this is 41 to the 1th times 41 to the 1/2. And when you multiply numbers with exponents, you add the exponents. So it's 41 to the 2/2 times 41 to the 1/2, and that makes 41 to the 3/2. Okay, cool, good, thank you, awesome. And okay, great. So it's never, if you get that, it's never going to get harder than that. I'm just going to repeat that now. 7 minutes. But now this time it's sine of the angle. So that's opposite over adjacent, over hypotenuse, not adjacent over. So now it's 4 over square root of 41, right? Yeah, and before it was 5, right? So now it's 2 times 10 to the 11th all over 263. Yeah. And that equals like 7.60 times 10 to the 8th newtons per coulomb. So that's the two components of one. Now we go to the other. I'm not going to draw the diagram because we're running out of time. E2x now, what will that equal? It will equal 1 times 10 to the 10th times the charge of number 2. Charge is now 2, not 5. And I'm not putting in the negative sign because I'm just looking at magnitudes right now. I'll put in the negative signs at the end when I use the arrows. All over, what's this? Well, it's 10 squared plus 3 squared, right? Times the cosine of the angle. So the cosine is 10 over square root of 10 squared plus 3 squared. So we get 2 times 10 to the 11th all over 109 to the 3/2 power. And that is like 1.75 times 10 to the 8th newtons per coulomb. That's E2x, right? And we have one last one to do, 4 minutes left. E2y, same numbers, 1 times 10 to the 10th times the same charge, which is 2, all over 109. But now times the sine of the angle, the opposite. So it's 3 over 109 square rooted. So we get 6 times 10 to the 10th all over 1.14 times 10 to the third. Six times 10 to the 10. Yeah. Um, and we get like 5.26 times 10 to the seventh, a much smaller number, which actually makes sense if you think about it. All right, so now you got we got 3 minutes left. We've got four numbers. What do? We got four components, horizontal and vertical of one and horizontal and vertical of the other. What do? We make an XY chart, just like we did in physics 203. And we just got to add them up. We're literally adding up the numbers. And if we run out of time, well, so we're going to add up the numbers. E1, I mean, I may go like a minute over. I encourage you to bear with me for like a minute just to get the final answer. But that, if you have to go, you have to go. But all I'm going to do is get the final answer so you see it and it just helps you with your home, whatever. So 9.51 times 10 to the eighth. And an E1Y is 7.60 times 10 to the eighth. And then E2X is 1.75 times 10 to the eighth. And the other one is 5.26 times 10 to the seventh. Now we're just going to add them up. But one thing before we add them up, now we look at directions. We look at those arrows we drew. Notice E1 was going to the west and was going to the south. So I put negative signs on those two. I'm still adding, but those get negatives because they're going to the south and to the west. So now I add everything up, right? I believe that's true. Yeah. Right. And I get 8.13 times 10 to the eighth. And so what do I do with 1 minute left with these final things? Wait, wait, something's wrong. Oh, no, I put the negative signs. Sorry. The negative signs are all, it's just about done, but the negative signs go all on E1. They're both, sorry. So I just did give me one. So we have one. So I put the negative signs all go on E1. It's too good to be true. 7 point. Okay. Okay. So, well, I'm going to say this in case you have to go. I'm just going to add them up. And what am I going to do with my answers? I'm going to make one big triangle. With the answers, I'm going to just make one big triangle, and the hypotenuse of it and the angle in it are my answer. If you can stay for a second, let me do it. But if not, you get what I'm saying, or you'll get the notes. I totally understand if people have to go now, but I'm going to finish this just so you see the answer. So, so I add up the E1 and E2. And I get negative point. That, yeah, this is right. And negative 0.07. Okay, so I have one big triangle that goes like this. It goes 7.76 to the west. And from that tip, it goes almost as long. It goes 7.7072 to the south. So my answer, the thing we were looking for all along, is this and this angle. So the answer E is the square root of the squares. And this is the answer. This is the answer. Like the magnitude of the E field is approximately 1.05 times 10 to the 9 newtons per coulomb. If I did the math, it's the square root of the squares of the 7.07 and 7.76. And the angle is approximately 43 degrees southwest. And that's the answer to the whole problem. And that means that every 1 coulomb of positive test charge that could ever be located at the origin would be pushed that amount of newtons with a force of that amount of newtons in that direction. And that's the answer. So I'll stop. So thank you for being, sorry. Okay, wait. So thank you for the correction. Oh, sorry. So you can leave, obviously, but if you're hanging out for a second, I'll answer questions. But yes, thank you for the correction. I think I made the correction that a direct chat person said. And then I'll stop. Well, I'm not going to stop the recording. How do I know which direction the vectors of the final answer will be? Literally thank you so much. Literally from the positive or negative signs. Like the final answers in my chart were both negative. Since the X direction was negative, I made it go to the west, and the Y direction was negative, so I made it go to the south. It's literally, and the does that okay, good. Okay, hold on, I'm just switching the. Does that make okay?
So
Okay,
you just look back at the compasses to see which one would like had the negative sign in which direction.
exactly.
Okay.
Okay, awesome. So good job. So I'm really glad you asked that perfect question you asked today. Um,
Thank you, Professor. Have a great day.
you too. Have a great break. Also, hold on. And anybody else? Uh,
Professor, I think that
yes.
my numbers were different than yours, but I'm not sure like when like they diverged. So can you flip back?
Yeah, I went really fast, or I may have made a mistake. Wait, let me just um should I turn off the record? I'm actually questioning whether I should leave the recording on or off for this because it might. Do you mind if I leave the recording on just in case this actually ends up
That's
fixing?
fine.
Okay, all right, thanks. So all right, so flip back. Okay, so where am I flipping to? Where am I how far back am I flip or where
Um, from I guess where you computed the vector for E1.
okay, so that's this right here.
Okay, let me see.
Oh, I hope. Oh, wait, should that have been a 5 and then a 4? Did I flip the fives and oh God. Maybe I flipped the 5 and 4 accident. Hold on one second. What's the coordinates of oh crap. You're right. I swapped. Wait, does this matter? Oh, it does matter. I'm not necessarily gonna change. Wait, did I think I flipped the 5 and the 4 accidentally. Hold on.
Okay, that makes sense because yeah, like if that's the case, then yeah, I noticed that the value for the total vector
Oh,
was
wait,
a little bit.
hold on. I'm sorry. Hold on. I don't mean to cut you off, but I'm saying that because I wrote it wrong right here, but I did
Mhm.
write it right. So I'm going to fix it right here. But it looks like somehow I knew that I'd written it wrong because if I go to the next page where I actually did the math,
Okay.
it looks like I actually did the right number. Yeah. So let's keep looking.
Okay, so I see, okay, for K, did you use 8.99 or did you use
Oh, well, so I rounded it. Oh, so all of our numbers may be slightly different because I did round it and I warned us of that at the beginning. And you're welcome to do this on the final. I rounded 8.99 times 10 to the ninth
Mhm.
to 9 times 10 to the ninth, which I then rounded to 1 times 10 to
Oh,
the
you rounded it to one. Okay.
yeah.
Yeah. Yeah, that would make it different. Yeah, so it's okay. Yeah.
But is your final, I mean, for example, is your final answer still pointing to the southwest?
Southwest. My final answer, I mean, it is a vector that has two negative values
Yeah,
in,
that's
yeah,
okay. That's what I mean. Yeah. So,
yeah.
and they're both like in the order of magnitude of like 10 to
Around seven-ish, yes.
okay.
Like,
So yeah. So then we're just I'm
yeah.
just because I hate these numbers so and you can do this on the final. I mean I severely round hoping to keep the numbers like somewhat manageable. There's still ridiculous numbers that but yeah, I'm rounding big time. So and if you did that on your exam and ours were different, you would still get full. I mean, I certainly am not going to take off for not rounding. So yeah, I think we're good.
Okay. Thank you.
Thank you. Okay, bye.
Bye.